Hi Samantha, I've got the questions that you sent here. This is a more efficient way of doing things for me because our time is limited in terms of appointments per week to most of the appointments are 45 minutes in length. So this is perfect if we can zero in on exactly what you're focusing on in class to get you ready for a quiz or whatever. Um, I think one thing that I find with statistics is that people often have trouble identifying which tests they need to use when they read a word problem. There's a few little key things that you can keep in mind when you're doing that. So, first of all, you probably will never use a Z-score because that's just taking like a single score, comparing it to a mean. So Z-score is probably not going to be something you're going to use. T-scores or t-tests are a lot more common, and there are three kinds of t-tests, and that's where it becomes a little more difficult because you need to identify which one you're doing so that you have the right formula. And so we have a dependent t-test, and a dependent t-test is when you have a before and after scenario, so it's the same group. You test them, then there's a treatment of some kind. Maybe you give them a pill that's going to make them more intelligent or something, and then you test them again, and so it's the same group that you're testing, but the difference is something has taken place in between, so you want to see if that made a difference with the same group. So that's dependent. Independent is when you have two different groups that you're comparing, and you also can have independent with the same variance or with pooled variance, where each group has different variance and you have to use the pooled variance calculation. You can also have a single sample t-test, and you would use that when you're comparing a sample to a population mean, and a t-test will work for small values of n, whereas a z-test you need at least n equals 30 for it to be valid. And so when we look at question 1, I think it's a lot easier to look at specific examples. So here's question 1 for us. And we have two groups. We have the older women and the younger women. They cannot be older and younger at the same time. So we know that they're independent groups. And they're giving us an n of 10 for each group. They give us a mean for each group and a standard deviation for each group. And so the first question is, using a hypothesis testing, do the groups significantly differ in their ability to identify items in the photo? So what we want to do here is an independent t-test in order to determine if there's a significant difference between the two groups. So that's always your hypothesis. The HO, which is the null hypothesis, is basically, however you want to state it, that the two means are equal, so mean 1 equals mean 2, or there's no significant difference between the groups. There's lots of different ways to state it. And HA, in this case, would just be that they're not equal, because it's just saying do they differ significantly, not that one group is better than the other. And so we could use a not equal sign here, and that makes it a two-way test, like a two-tailed test. Either one group could be lower than or higher than the other group. So the only time you're going to use an equals is when you're doing the null hypothesis. You're not allowed to use an equals in the alternate hypothesis. Only greater than, less than, or not equals for those statements. I'm going to assume that you're allowed a formula sheet because you've got the formulas here that you've provided. And in this case, because our standard deviations are different, we would have to use the calculation for the pooled variance for both of these groups. And I don't see that formula on your formula sheet, so that's making me just wonder a little bit. It's sometimes hard if I'm not in your lecture to know exactly how they're presenting material to you guys. My mistake, sorry, I do see it on the other side here. So they're giving you the pooled variance formula, the SP squared. And so you're going to calculate that, and that's just that with all the t-tests you have degree of freedom, so whatever n is, you're going to subtract 1 from it. So we have an n of 10 for both groups. So we would have 9 times the first variance squared, the first standard deviation squared, which is 6.96. And then we're going to add to that 9 for our degrees of freedom again, times the second standard deviation squared, which is 4.52. And we're going to divide that by the total degrees of freedom, so that would be 20 minus 1 minus 1, so that's divided by 18. So that's how you get your pooled variance. Then we need the standard error, because that's what goes into this formula, and so we're going to take that between the two means, and that's going to give us our pooled variance over n1 plus our pooled variance over n2. So that's going to give us our SP squared over n1 plus SP squared, the one that we just calculated above, over n2, and then we're going to square root that. That's our standard error. So when we put it into our t-test, for our independent t-test, then we can take the mean value, so 18 minus the 12, over our, sorry, that should be x1, x bar 2, like that, and we're going to get a t-value, and then we can compare that to the t-crit for, if it doesn't state otherwise, for alpha, alpha, no, that's not right, sorry, I had it right the first time, alpha equals 0.5, or 95%, okay? And this is a two-tailed test, like we said, because it's just not equal. It's not greater than or less than. Okay. Just to save a bit of time, I'm not going to do all the calculations. I'll leave that up to you. I'll just set you up, and if you have trouble with those, you can always email me later, okay? So let's just move that. Oh, I want the whole thing to move up here. Sorry. Okay. And so it says calculate and interpret the 95% confidence interval. So for an independent t-test, when we do that, what we're going to do is take the difference in the means. So that's just x bar 1 minus x bar 2, like we used in the previous calculation. And then from that, we're going to add and subtract, so plus or minus, the t-crit value. So that's the one that you looked up previously that you're going to look up for a two-tailed test at alpha equals 0.05, and you're going to times that by the standard error that we calculated up here. This is our standard error. Okay, so what that's going to do is give you the difference between the means plus the error for our confidence interval. This whole thing is going to give us the error, and the difference between our means minus the error. So we're going to get a range, and we usually write confidence interval. Now, again, it depends on who's teaching this, and I know you're taking it in Durham, and they've just revamped the whole course in Peterborough. So there's an APA format to writing the 95% confidence interval, and a lot of times when you're doing a assignment or something, you would write it like that, and you would write it in interval notation. So let's say that it was, I don't know, like 4.5 to 7.5 or something like that. You could write it like that, and that would be your confidence interval. It's just giving a lower value for the range, like the minimum, and the maximum value for the range. And as long as we stay in that range, we're 95% confident that our mean will always fall somewhere in between those. For the next question, they're asking about the power, and how we calculate the power is we need our t-crit value, and so I'll actually write it in here so that we have it to work with. Our t-crit value for this particular test is 2.086. When you have a t-value, you always take the absolute value of it, and what that means is if it turns out to be negative, you just use the positive value of it anyway. So our t-crit value, if we set our independent t-test equation equal to that, and so we have 18 minus 12 on top, so that would be 6 over the SE, then what we need to find, is actually what value of the two means being subtracted will put us just over or just under that t-crit. And so you're going to solve this equation for the top, for the numerator, and that's going to give you the value that we need to reject the null. So this part is a little confusing for people when they're first learning to find the power, but whatever value we get for the x bar 1 minus x bar 2, that is going to be the value that would make us reject the null. So we're going to take whatever value that is, and we're going to subtract 6, which was the original difference between the two means, and we're going to set that up as a z-score, where we're going to take this value first, minus 6, so this one comes in here, minus 6, all over our standard deviation that we calculated for the pooled variance. And so if we do that, we're going to look up the p-value in our chart that we get from this, and then we're going to do 1 minus that value. So 1 minus the p-value from our z-score calculation. That will give us the power for this calculation. For Cohen's d, for the effect size of the difference, it's just a z-score, and so we call it a d value, but we're going to just take the difference between the means, and we're going to divide that by the pooled variance that we calculated earlier. I'm going to put sx1 minus xx2 like that. And so whatever we get there, you can use your chart that tells you whether that's a large effect size or a medium or a small effect size. And that's what they mean when they say interpret. You're just going to say small, medium, or large. In question 2, this word here is your keyword that's going to tell you that we're doing a chi-square comparison, because chi-square takes observed versus expected values. And so when we're calculating that, what I've done is I've written out the actual observed values, the number of people, and it turns out the total was 100, which was nice of them because that makes it easy for us to do our percentages. And we're going to compare those percentages to the ones given in the claim, and that's all of these values up here. And we want to see if that observed versus expected is within the normal range, and that means no difference between them. And so our chi-square formula is just the sum of all of the observed minus the expecteds squared over the expecteds. And so in this case we have 4 different things that we're measuring, because 4 different blood types, and so we're just going to do observed minus expected. So 38 is observed, and expected was 44 over 44, like that. Then we're going to add observed minus expected for the next blood type, for type A, and so they were expecting 41% for that one, and they observed 38, so we'll do 38 minus 41 over 44. We're going to keep going. For type B, we were looking at 10%, and what we actually observed was 20. And so we're going to put that over 10 for the expected. Oh, I think I made a mistake. I'm sorry, that should have been 41. And then the last one that we're comparing for the type AB, we're expecting 5%, but we observed 4%, so we're going to do 4 minus 5 over the expected, which was 4. And so the sum of all of those is just adding these things together, and so we end up here with minus 6 over 44, plus minus 3 over 41, plus minus 10 over 10, plus minus 1 over 4. And then we need to square those values on the top, and that's how we get rid of our negatives. And so what we end up with is 36 over 44, plus 9 over 41, plus 100 over 10, plus 1 over 4. So we're going to add those up. You can use your fractions calculator if you want to, and we're going to get a pretty high chi-square value. And then all we have to do is compare that to the chi-square value, the critical value from the chart. And so when we go there, we're going to look for the number of columns is 4. So our degrees of freedom will be 4 minus 1, which is 3. So we have degrees of freedom equals 3. And if they don't give you a significance level, then we assume alpha equals 0.05. So you're going to look up your chi-squared crit value, and you're going to compare it to the value that we calculated, and you're going to make a decision on whether to reject or fail to reject the null based on that, and then you would do a final word answer, therefore I would not expect this to happen, or therefore I would expect this to happen. Okay, I might divide this video off into 2 just because it's getting pretty long. So part 3, question 3, this is a dependent t-test, and the reason we know it's dependent is that it's the same group, okay? So these people have been selected, something's been measured, which is how many cigarettes they smoke per day. Then there's a treatment, they're shown a video, right, a campaign, advertising campaign, and then they're measured again after that treatment. So that's how we know that this is what we call a dependent t-test. And so you're going to use the formula for dependent t-test here. And so on average, the smokers reduced their daily smoking by 10 cigarettes with a standard deviation of 3.5. And so what they've done is they've done the calculation from that formula for you of the D bar minus the population mean here. So they're saying that it's gone down by 10 cigarettes. And our standard deviation is given, and the standard deviation is given at 3.50. And so when we calculate our t-score here, then we're going to do a t-score for minus 10 over 3.50, and there's 15 smokers in this group, so our degrees of freedom is 15 minus 1, which is 14, and we're going to look up alpha at 0.05 for the one-tailed test, because we want to reduce, we want them to have less cigarettes smoked after the treatment. So in order to determine if it's a successful campaign or not, we're going to get our t-value, we're going to compare it to our t-crit, and we're going to decide whether to accept or reject the null hypothesis, or as they say, reject or fail to reject the null hypothesis. And that would be the answer to A, because they're asking if the campaign was successful, and if that's the case, then we would reject the null and say that there was a significant difference between the before and the after groups. And then in part B, we're back to having to interpret the power, calculate and interpret the power. We're going to do that the same way that we did in the previous test. What we're going to do is we're going to find the actual value of this that would make us cross that threshold for the t-crit. And so we're going to set that over our SD equal to t-crit. And whatever that value is, that's what we're going to use. We're going to take a z-score. We're going to take that value minus the original mean value, which was, I don't think they gave us the original mean in this one, did they? Sorry, we don't need the original mean. We need the difference between the means, which was that -10 value. And we're going to put that over our standard deviation. And then we're going to look up the p-value that we get from that z-score, and that's going to give us the power. And again, interpreting the power is small, medium, or large. For power, it's the probability of making a type 1 error in our evaluation of our hypothesis. So we have to say that that's the probability, whatever that value turns out to be.